Hello, my name is Steve Nils and I work as an area coordinator for the Further Maths Support Programme in Wales, and I'm based in Aberystwyth University. If there is anything that appears on the slides during this presentation that you would like further clarification of, you can contact me on either of the two email addresses that are on slide 1. Now, for this session, I intend to look at some of the topics from pure maths, in other words, unit FM1 that you have looked at this year, and see how they are developed and then used in units 4, 5 and 6. Now, some of the topics will have a greater application either to unit 4 or unit 5 or unit 6. So again, it's worth having a look at all of these topics. Now, as far as mathematicians are concerned, one of the biggest things that we like to do is to prove something for every single number. And this concept of proof is very, very important. Now, one of the major things that you looked at in FM1 was a topic called induction. Sometimes you can think of induction as a leap of faith, but it's about proving something for every single value. Now, if you think about the work that you've done already during your school careers, you will have come across Pythagoras' theorem for a right-angled triangle and Fermat's last theorem that says that if you go above Pythagoras' theorem, in other words, x squared plus y squared equals z squared, it doesn't work. Now, the proof of Fermat's last theorem was proved towards the latter end of the 20th century, approximately 350 years after Fermat first proposed it. So they actually work for every single value. Now, there is another mathematician called Goldbach, spelled Goldbach. Now, unfortunately, Goldbach only has a conjecture. Goldbach's conjecture is that after the number 2, every even number can be written in at least one way as the sum of 2 prime numbers. Now, as I've said, this is known as Goldbach's conjecture, and it is a conjecture because we cannot prove it. Now, it's not so much that we can't prove that an even number is the sum of 2 primes. Where Goldbach's conjecture fails to become a proof is in terms of we don't know all the prime numbers. There isn't a rule that will generate every single prime number for us. There are rules that will produce quite a number, but there isn't one generic rule that produces all of them. For those of you interested in number theory, if you can ever come up with that, I believe there's quite a substantial prize for whoever can come up with a solution to that. So induction is looking at how we prove something. Now, induction, as you came across in FM1, has 4 main aspects. Now, those aspects, and as it says it looks at proof, are the basis, the assumption, the inductive, and the conclusion. Now, the basis, hopefully, should be quite simple. They give you an expression involving n, and you literally, for the basis, just say, well, when n is 1, we get this. Step 2, we replace n equals 1 with n equals k, and that's our assumption. And then comes the leap of faith, the inductive part, that we replace k with k plus 1, and we show that we end up with the same form with the expression. Now, this concept of induction is also known as the domino effect, because if you knock the first domino over, it will fall. So it will hit into the second domino and that will fall, and that will in turn hit into the third domino and that will fall. So the whole concept behind induction is similar to the child's game, the domino race, and you knock one and they all consequently fall down. The conclusion, the general statement at the end, that can almost be thought of as a copy and paste, because the one or two sentences that you need to put in for the conclusion, they should be the same for every single induction question. So it's a case of just learning that and reproducing it. Now, one of the questions that you perhaps have looked at is the one from 2019, and it says prove that 9 to the power of n plus 15 is a multiple of 8. So we need to go through the 4 steps: the basis, the assumption, the inductive, the conclusion. And it might be worthwhile as you're working through this to really, as you're doing your solutions, to say, right, I'm doing the basis now, and write the basis down. So it would look something like the following. So the basis, just get this right. When n equals 1, we've got 9 to the power of 1 plus 15 equals 24. Which is a multiple of 8. So we can say, therefore, the proposition is true for n equals 1. So that's our basis. You literally put n equals 1 into the question and it should come up with a multiple of 8 in this particular case. Now is the assumption. So for the assumption, so the assumption, we have assume true for n equals k. So i.e. 9 to the k plus 15 is a multiple of 8. Well, rather than have it in terms of words, it's much more convenient if we write it as or 9 to the power of k plus 15 equals, and then we'll call it 8 let's use capital N. Don't use the lowercase n. So that's equation 1. So we're claiming that 9 to the power of k plus 15 is a multiple of 8. Well, if it's an 8 times table, it's 8 times a particular number. So that's where equation 1 comes from. So now we need to move on to the inductive phase. And for the inductive phase, what we have there is we replace k with k plus 1. So we're going to say consider n equals k plus 1. So that's the next number in the list. We've proved that, if you like, item 7 has collapsed. So let's make sure that item 8 collapses, the dominoes. So that will give us 9 to the k plus 1 plus 15 but 9 to the k plus 1 from the work that you've done in Unit 1 of your Mathematics A level and the work that you've done at GCSE, that is in effect 9 times 9 to the power of k. Remember, we add the index numbers. So again, as with all things mathematical, you're building on the work that you've done previously. You can't just ignore it. Now, from equation 1, 9 to the power of k is 8n minus 15. And then we put the plus 15 on the end. So removing the brackets gives me 72n minus 135 plus 15. Which is 72n minus 120. So looking at that, the right-hand side of that expression is 72n minus 120. Both of those numbers are multiples of 8. So we've got the right-hand side is a multiple of 8. So that means that if the right-hand side is a multiple of 8, therefore the left-hand side is also a multiple of 8. So that's our leap of faith. That's our inductive step. So now all that's left is the conclusion. And the conclusion is basically a series of statements. So for the conclusion, what we have is if the proposition is true, for n equals k, it is also true for n equals k plus 1. So, as we've shown it true, for n equals 1, by induction, it is true for all positive integers n. For all is the upside down capital A for all positive integers n. Now, as you can see, there's very little writing here. There's enough, but the important thing is that that statement can almost be copy and pasted onto the end of any induction question. There's no reference to 9 to the power of n plus 15 whatsoever. Now, it doesn't matter here if we're talking about an induction question just with numbers, whether we're talking an induction question with matrices, that doesn't refer to the question at all. So that's quite nice. You need to learn that and make sure that you can reproduce those few statements. So that's the concept behind the induction. Now, part of the reason for going back and looking at induction is that in FM4 you are going to use induction again. But when you move on to FM4, the big focus is in complex numbers, dealing with a topic called de Moivre's theorem. I'm not quite sure if my pronunciation is right. I've heard it pronounced about 5 different ways. So de Moivre's theorem. Now, it's to do with complex numbers, and it can be applied to both the trig form and the algebraic form. Generally, it tends to work better with the trig form. Now, again, just as a reminder, the two algebraic and trig forms are as they appear on that slide. The algebraic z equals x plus iy, where I is the square root of -1, and for the trig form, z equals r, open brackets, cos theta plus I sin theta, close brackets. Now, with de Moivre's theorem, it actually states that if you have cos theta plus I sin theta to the power of n, that is similar to writing cos n theta plus I sin n theta. Now, technically, you would have r times there, so it would also be multiplied by r to the power of n. Now, in terms of induction, the proof of this will come up in FM4. What I want to do is just say to you, look, this is coming up and it will help you in terms of understanding how numbers fit together. Now, if you look at the roots of an equation, so say for example, you want to find the nth root of an equation. Now, generally up to about now, we've looked at finding square roots and cube roots, and occasionally you might have dallied at looking at what's the fourth root. Now, by using de Moivre's theorem, it's much easier to find the fourth, fifth, sixth, seventh, eighth roots, and you can go higher if you so wish. But again, it's all well and good finding these roots of the equation, but what are they? How do we interpret them? Well, we can look at them geometrically. And if, for example, you find the cube roots of a problem, that should give you 3 answers. Now, the fact that you've got the 3 answers, if you plot those 3 answers, and we're specifically looking at complex numbers, so you're going to plot those 3 answers onto an Argand diagram. You plot them onto the Argand diagram, and if you join those 3 points up, you will end up with an equilateral triangle. Now, move on a step. If you find the 5th root of a question, you will end up with 5 solutions. Consequently, you end up with the 5 vertices of a regular pentagon. And if you find the 8th root or 9th root, usually odd numbers work better. But if you find, say, the 9th root, then you'll have the 9 vertices of a regular nonagon. So we can actually interpret it that way. Now, as an example of that, if we look at finding the cube root of -3, so our complex number is going to be represented by z. Now, when you find the roots of a problem, in this case, we've got that z equals -3 to the power of 1/3. So that in turn will give me that z cubed equals -3, and that z cubed plus 3 equals 0. Now, one of the things as an A-level mathematician, you need to be able to factorize a cubic, especially if it's only got 2 terms. That's almost like saying to a better GCSE student, you need to be able to apply the difference of 2 squares. Now, in terms of this, you take the cube root of each item, so that will give you z plus 3 to the power of 1/3 in the first bracket. Now, if you notice, the equation I was factorizing was z cubed plus 3. My first bracket is the z plus the cube root of 3. If my term was z cubed minus 3 equals 0, my first bracket would contain the minus symbol. Right? So they link up. There is a link there. Now, my second bracket is z squared minus z 3 to the 1/3. So it's 3 to the 1/3, not the z. And then finally, plus 3 to the power of 1/3 squared. So that'll be 3 to the 2/3. That equals 0. So now you're almost back at the work you were doing at GCSE, that you're saying, right, I know it was a quadratic there, but effectively when you factorized your quadratic, you had two brackets. Those two bracket terms equal 0. So that means one or the other or both equal 0. And we're going to apply the same principle here. Either the first bracket is 0 or the second bracket is 0. Now obviously the first bracket being 0 is quite nice and easy to solve. So that will give us that we have z equals minus 3 to the power of a third. And it's going to be there. Okay, so we've got z 3 to the power of 1/3 and we've moved it to the right hand side. The other part is we are going to need to solve z squared minus z times 3 to the third plus 3 to the 2/3 equals 0. Now that's a quadratic in z, and again you've had a lot of experience of solving those. So if we take the second one, obviously on that second expression, a is 1, b is minus the cube root of 3, and c is 3 to the power of 2/3. So if we look at our quadratic equation, that will give me z equals 3 to the power of a third, because it's minus b, so b is negative, minus minus, it is, plus or minus 3 to the third, and that's going to be squared, that's your b squared, minus 4 times 1 times 3 to the 2/3. That's inside the square root. And that's all divided by 2. So that will give me 3 to the third plus or minus 3 to the third squared is 3 to the 2/3. It appears in both of those items, so I can take that outside the square root, and I'm left with 3 to the 1/3. And then inside the bracket, I'm left with the square root of 1 minus 4, which is minus 3. And that's all over 2. So therefore, z equals 3 to the third plus 3 to the third times 3 to the half I, all divided by 2, because the square root of minus 3i is 3 to the power of minus 3 is 3 to the power of half I, or z equals 3 to the third minus 3 to the third times 3 to the half of I, all divided by 2. And then from the previous slide, we've got or z equals minus 3 to the third. Now, as you can see, based on the work that you've done in FM1, I've got 3 solutions. I should have, because it's a cubic. Power of 3 gives me 3 answers. Power of 7 gives me 7 answers. But if you notice, I've got one real answer, the negative cube root of 3, and I've got 2 complex answers. And the big thing to remember is, in this situation, that my answers are, if you think back to the work you did on FM1, they are complex conjugates. So again, when I multiply those 2 together, I am going to end up with a term which does not contain imaginary numbers. There are no I values involved in that. Now, in terms of that, if we look at how we plot that on a graph, or more importantly, an Argand diagram, those are my 3 points. You can see by the green arrows. The arrow going straight left, that's the real part, that's the cube root of minus 3. And then the other 2 are the cube root of 3 plus or minus cube root of 3 times the square root of 3 of I. So if you join the ends of those 3 green arrows, you will end up with an equilateral triangle. And again, because it's the cube root, 3 roots, we only end up with 3 green lines. If we were finding the 5th root, we'd go through the same process and you would end up with 5 lines in green, therefore the 5 vertices of a regular pentagon. So again, that's where it's really, really useful and important, in that it can be used and you can demonstrate and show what it looks like. Now, again, you'll spend quite a bit of time looking at this, so you can see that the people that have come up with the courses, they are very keen on you understanding what it looks like as well, and the graphical representation, so it is important. Now, the next topic I want to look at is the one on matrices. Now, in terms of the matrices, when you were looking at matrices in FM1, you looked at 2 by 2 matrices, and in FM4 you're going up to look at 3 by 3 matrices. Now, in terms of that, the concepts and ideas that you were looking at, things like finding the determinant, finding the inverse and so on, you have to do those for 3 by 3, 4 by 4, 5 by 5 matrices. We tend to try to end up with square matrices. It's not always the case. The ideas you learned for 2 by 2 matrices, they will be extended and used on 3 by 3 matrices. Now, in terms of a 2 by 2 matrix, if you've got that matrix there, the matrix A, find the determinant of 1, minus 4, 0, 3. Now, determinant, at the moment, as that's written, that is a matrix because it has a curved bracket. To find the determinant, I need vertical lines. So, if we look at this question, what we've got is we want to find the determinant of A and that is 1 minus 4, 0, 3. Vertical line, vertical line. So that equals 1 times 3 minus 4 times 0. And that obviously is 3, take away 0, so I have a determinant of 3. Now, when I introduced the round brackets for the calculation, I did the first bracket minus the second bracket. And we'll come back and have a look at that in a bit more detail in a moment. But it's looking at those particular signs and how they are put through the matrix. Now, if we proceed and then say, well, okay, how do we find the matrix of this one? The determinant is going to be a little bit trickier. Now, if this is, we'll call this one matrix B. So for matrix B, we want determinant of B equals, and it's 5, 2, 1, 0, 6, 3, 8, 4, 7. Now, consider if I only have the top left 4 numbers. So if it was 5, 2, 0, 6, we were finding the determinant of that. Unfortunately, we've got a 0 in it again. It's 5 times 6 minus 2 times 0. And again, I've introduced the minus symbol there. It's because what we're doing, if I write it in red, we have here. What we have is the following. Plus, minus, minus, plus. So the number in the top left is a positive. The next number across is a negative. So if we then go back to our 3 by 3 matrix, what we have there is plus, and then the adjacent ones to the plus are both minus. Then adjacent to the minuses, we have pluses. So it alternates from plus to minus and back. That's going to be a minus, that's going to be a minus, and that's going to be a plus. So the top left, if we start there on the matrix, the top left number is defined as being a plus. Even if it's minus 5, you would say add on, open brackets, minus 5. So we always start top left with a plus symbol. Now, in terms of how do we actually find the determinant itself, what we have there is the determinant of B is equal to 5 times 6, 3, 4, 7. Minus twice 0, 3, 87. And then plus 1 times 0, 6, 8, 4. So as you can see, starting top left, plus 5, minus 2, plus 1, plus minus plus. Now, again, how do we get the numbers inside the lines? Now, if we think about, and I'm going to write it down 3 times, we've got 5, 2, 1, 5, 2, 1, and 5, 2, 1. Next line is 063, 0, 6, 3, 0, 6, 3, 0, 6, 3, and the bottom line then is 847. Now, what we're in effect going to do is, I'll do the first one in red. That's our first number 5. So what we're saying to ourselves is anything in the same row, I ignore. So basically I'm crossing out the 2 and the 1. And anything in the same column as the 5, I'm going to ignore. So we cross out the 0 and the 8. So we're then almost saying find the determinant of 6, 3, 4, 7. And then moving on to the second one, we do the 2. We ignore the 5, and we ignore the 1. And similarly, we ignore the 6 and the 4. So they've gone. And then finally, if we move to the yellow, we circle the 1, we ignore the 5 and the 2, and we ignore the 3 and the 7. So that's how we get each of those. So that one goes to there. The blue goes to there, and the red goes to there. So you can see how those 3 link together. So again, what we've learned for a 2 by 2 matrix, we now apply to a 3 by 3. We just ignore one of the lines and one of the columns. Now, the obvious question is, does it give me a different result if I pick the middle row? So instead of having 5, 2, and 1, what if I have 0 outside, 6 outside, and 3 outside? Or what if I pick the bottom row, 8, 4, and 7? Well, that's something for you to try. Does it give me a different solution? The simple answer is no, it doesn't. That's for you to investigate. Now, if we look at the final solution for this, what we've got is the determinant of B is 5 times 42 minus 12 minus 2 naught minus 24 plus 1 minus naught minus 48. And that's 5 times 30 minus 2 times minus 24 and plus 1 times minus 48. So by pressing a few buttons on your calculator, that gives you 150 minus minus is plus 48 minus 48 which is 150. So quite a large number, but given the fact that they're all positive numbers and some of them are getting quite large, close to 10, that would explain why the determinant's 150. So that's the answer. And again, if you work out either along the middle row or the bottom row, you'll find you'll get the same answer. As I mentioned just now, you can do all the calculations on your calculator. You've obviously learned from your lesson so far that you can use your class whiz calculator to actually work out the determinant without going through all this process. So to do that, you would actually, once it's switched on, you would press the menu button, and then option 4 for matrices. Having done that, you click on define a matrix, and you will enter option 1, and that will be a 3 by 3 matrix. So number of rows is 3, and then number of columns is 3. And then you'll cancel AC. Now, having done that, you will then press the option button, and then you'll press the down arrow button. That will take you to a second page, and on that second page you will want to press 2, which will enable you to find the determinant. There is also a button on there that will allow you to find the inverse straight away, but I'll come back to that in a moment. Having done 2, find the determinant, we'd press option, and once we've pressed the option button, it comes up with a couple of choices and then the 4 matrices that you can define. So if it's only the one matrix, it'll be option A, so that will be number 3 on the buttons that you press there, and then just press equals, and that will give you the answer of 150. Now, I appreciate at the first instance it seems as if there's a lot to say, oh, I could do this, but I think quite often now you've got the technology, it doesn't take long to actually get used to using it. In terms of finding the determinant, it is very, very useful to go through this process about how to find the determinant. It's all well and good pressing the buttons on the calculator and out pops the answer. That's fantastic. The only problem with that is that you don't have the understanding of where things come from and how they fit together. And as you move through the course, sometimes that's where you need to improve your knowledge base, is how does it work and why does it work. So going through the 3 slides, that's how and why it works. But at the end of this 3rd slide, if you like, that's the shortcut option. So if you were in an exam, you need to read the question carefully. If it says things like showing all your workings out, then working it out on the class whiz isn't of much use to you. Now, in terms of matrices, it's all well and good saying, yes, we can find a determinant and the inverse of a 2 by 2. We can go on and look at the determinant and inverse of a 3 by 3. But in one sense, why? Why are we doing it? Where is it useful? Where is it helpful? Now, if you think about matrices, you can go all the way back to year 10 and start looking at simultaneous equations. If you write them as a matrix equation, then with some simple row reduction, you can actually work out what the values of x and y are. Again, you need to be very, very careful as to which particular group you're working it with, but you can actually do this with a year 10 group. But that's only obviously up to 2 or 3 unknowns. So you're talking about 3 planes, 3-dimensional space, and that's stuff that we can all visualize. But we can also use matrices when we start looking at things like string theory. So those of you that are thinking about physics, then string theory works usually in 10 dimensions, or as it's saying there, the M theory, which goes up to 11 dimensions. Now, trying to visualize that sometimes is incredibly difficult, but at least with matrices, we have the facility to solve problems, to work out the numbers, and we can go from there. So in that sense, it's an incredibly powerful tool that can help us in other aspects of our life. If you go into engineering, obviously you're talking about problems with lots and lots of different unknowns. Again, if you can write them as matrices, then it hopefully will make the work much, much easier for you when it comes to it. So again, matrices, they're nice to study in their own way, but they are useful once you step outside of pure maths. And I think that's the important thing. Pure maths is mathematics just for the sake of it. And quite often, we're more interested in where can I apply it? Does it come up in statistics? Does it come up in mechanics? Where? And so that's the big thing, is appreciating that what you learn in core, the pure maths, can be used to make the applied maths easier. Now, in terms of the next topic, which is differential equations, it can be used both in statistics and in mechanics. So it's a case of where it can be used in both. Now, as far as mechanics is concerned, that generally applies to motion. As I've said there, it can be motion in a straight line or motion that they call SHM, which is simple harmonic motion. Engineers use differential equations when they look at the flow of a fluid. Now, that could mean the flow of a fluid down a tube. So it could be water through a tube. It could be oil in an oil refinery flowing through a tube. It could be blood in veins and arteries flowing through the veins and arteries. So we've got all those things, but it can also be the motion of gas. One of the best examples of motion of gas is aeronautical engineering. How to look at the way the air moves around the airplane as it's flying. Another application of the motion of air past an object is in Formula One car racing, that they were finding at one stage that the cars were starting to move that fast that they've designed the cars now with what is known as downdraft. Now, prior to the days of downdraft, when the cars were going quite quickly, if a bit of air got in underneath the front of the car, it would lift the car up. There are some films of people doing it on boats, racing across the water, and the front end of the boat lifts up. So with a car, they've designed cars now to take into account the flow of the air over the car, and it produces what is known as a downdraft. So it almost sticks the car to the road, and it's very difficult for the car to lift off. So again, engineers are looking at the flow of fluids, and quite a number of universities offer courses on differential equations. Quite often they're offered by the mathematics department, and engineers and physicists will also come in and study those courses as well. So they are very, very important in terms of solving things in mechanics. If you look at statistics, then you're looking more then at the integration and finding cumulative frequency distributions and along that sort of way. So even things like the standard normal distribution, you have what is really a very awkward and nasty looking equation that needs to be integrated, which is differential equations. So we've got all those different aspects as well. Now, what's on the screen at the moment are just examples. They are not related to one another. So the equation on the right-hand side is a differential equation. That is called a second order differential equation because it's got y double dash. So that's like acceleration minus 7 times velocity plus 12 times distance equals 0. Right? That's what the double dash is, to put it in terms of mechanics. The picture on the left is a surface. Surfaces can be mapped by using differential equations. So the actual equation for that surface is quite complicated, but I just wanted you to see that differential equations isn't just an equation. It can be brought to life in terms of surfaces and what they look like. Now, you've looked at differential equations already in that you've done Unit 1 on your Mathematics A level, where you did basic integration of polynomials, and you started off when you integrated, you just had what is known as the constant of integration. And then after a little while you said, right, when this happens, we have this particular value, find what c is. So it might say when x is 2, y was 5, find the value of c, and then go back and rewrite y equals. And you did that. When you looked at FM3, you were integrating vectors, and quite often you were integrating vectors involving trig functions. And when you integrate a vector, the constant of integration must be a vector. It cannot be a scalar. And that's the other thing you need to be very, very careful about. That when you're writing your vectors, that you need to make sure that you can tell the difference between a vector quantity and a scalar quantity. So we need to be very, very careful as to how we're writing those. So with that, we've got this constant of integration which we need to calculate. Now invariably, when we go to calculate this constant of integration, it is quite described as either the initial conditions or boundary value conditions. Now an example of that would be, you need to read the question carefully, because if it says a particle starts from rest, then the boundary conditions are when t equals 0, v equals 0. Nice and easy. Now, those of you that are aware of the work that Swansea University have done on thrust SSC, which is the new high-speed car that they're trying to break the world land speed record with. When you break a world land speed record, they time you over a quarter of a mile, and then you have so many hours to turn the car around, refuel it, and go back the other way. But you don't time it from a standing start. You have two poles, quarter mile apart. The car comes past, electronically triggers the clock, and as it passes the second one, the clock stops. And it comes back and it does the same thing. And then they average out the speeds from those two runs. So in that sense, the clock starts t equals 0. The car isn't from a stationary point. The car at that point, they're hoping, could be moving at 650, 700 miles an hour. So the boundary conditions there are, when t equals 0, v equals 650 miles per hour, for example. So we need to be very aware of what it's telling me in the question. What's the value of t and what's the corresponding value? Now, as I say, we've met this when we've been integrating vectors. So if we look at this, given the equation that we have there, that r double dot, the acceleration, is 4t minus 3 in the I direction plus 6t minus 2 in the k direction. The boundary conditions are when t equals 0, v equals 2i minus 3j. And then we've got to go on to find r. If you notice, rather than write them in bold print, I've written the vectors there and I've underlined the vectors. I cannot stress this enough, that you distinguish what is a vector, what is a scalar. I know that in some places, vectors, they don't underscore, they overscore. They put the line above it. It really doesn't matter, but please be consistent with what you are doing, right? And I think that's the big thing that you need to think about in terms of vectors. Now, in terms of this, if we imagine that r double dot is the acceleration a, then v is the speed. And what we need to do is we need to integrate the acceleration to find the speed. So what we have is that v equals r dot, which is the integral of r double dot dt. So therefore, v equals 2t squared minus 3t and then plus 3t squared minus 2t k plus my constant of integration c. And it is a vector because c has a component in the I direction, the j direction, and the k direction. Now, my boundary conditions, when t equals 0, v equals 2i minus 3j. But if you apply that to that equation, that v is that, so 2i minus 3j equals 0i plus 0k plus c. So v equals c. So therefore, v equals 2t squared minus 3t plus 2 of I minus 3j, and then finally plus 3t squared minus 2t of k. So that's the value of v, and we've used the boundary conditions. You're then asked to find the displacement vector r. So therefore, r is the integral of v. So r equals the integral of v dt. Remember, t isn't a vector, so it's not underscored. So if we work that out straight away, that is 2t cubed over 3 minus 3t squared over 2 plus 2t of I minus 3t of j, and then plus t cubed minus t squared of k. And because we've integrated, we need a constant of integration, which is c. And again, it's a vector component, so it's underscored. Again, put in our initial conditions or boundary conditions. When t equals 0, r equals I plus j plus 2k. And that must be equal, because we've substituted, to the value of c. So therefore, r is equal to 2t cubed over 3 minus the 3t squared over 2 plus 2t plus 1. And that's of I, and then plus, and I'm going to write it as 1 minus 3t of j, and then plus t cubed minus t squared plus 2 of k. So you can see there that we've dealt with these boundary conditions so that we're always taking into account the information that we've been given in the question. Now, as far as these topics are concerned, again, it's just a little taste and flavour of what you've met and where it's going, so that it's just enough, hopefully, to pique your interest. With matrices, it's worth going back, checking, is the determinant the same if I work across the second one? And remember, the second one is minus plus minus, so that you can see it.